It's not terribly intuitive, it is a little bit difficult to understand, but if you keep with it, I promise you it's worth it. It unlocks virtually all of modern physics, particularly astrophysics, is associated with general relativity.
Hi everybody from the wonderful city of Wuhan today with an equally wonderful video, I hope. One of the most important theories in all of physics, and that is general relativity. Now, a lot of you have asked to understand things about gravitational lensing, dark matter, dark energy, expansion of the universe, so on and so forth. All of this comes from general relativity. And so before we talk about that, we need to tackle general relativity. What is general relativity? General relativity is the theory of gravity. And let me give you the answer first. It is that gravity is equivalent to curved spacetime. Now, that may sound like a bit of nonsense right now, but let's explain how Einstein gets there and what its importance and significance is. Now, Einstein starts his theory of gravity with some very straightforward observations that I can share with you. The first observation is this. When you stand on the surface of the Earth and you throw a ball, you know that it moves in a parabola, by which I mean it goes like this. Einstein's first insight, called the elevator thought experiment, is that if you place an elevator in a vacuum in space, far, far away from any planet or gravitational field, and you accelerated that elevator at constant acceleration, and you threw the ball, you'd see the same path. In other words, the constant acceleration is the same as a gravitational field. Alternatively, and somewhat morbidly, it is said that he was one day sitting in his patent office in Bern, looking outside at workmen on the roof of a building next door, and he imagined if one of the workmen in his toolbox fell off the building, that workman, as accelerated towards the ground, would effectively feel weightless, would feel that there is no gravitational field. You would have had the same effect, for example, if you'd been on a roller coaster, and would see the objects that are falling down with him as stationary, in other words, also as if there was no gravitational field. Now you may think, so what? This isn't like that great, but it is a big insight. What it tells you is the equivalence between acceleration and gravitation. And that's important because that doesn't exist for other forces. And it shows you that gravity is actually a very special force. And this is called Einstein's theory of equivalence, the equivalence principle, which is that locally, uniform gravitational fields are the same as constant acceleration. That's insight number one. Now, how do you get from this to curved spacetime? Well, you get there by having to consider things called tidal forces. Tidal forces are basically where gravitational fields are non-uniform. So the gravitational field of the Earth is non-uniform, by which I mean that the gravitational field of the Earth is stronger as you approach the center of the Earth. It's weaker as you move away from the Earth. Now, why does that pose a problem? Well, it actually poses a problem for Einstein because it means that you can tell the difference between these experiments done in an elevator and the Earth's gravitational field. And you remember the equivalence principle was that you can't tell the difference between acceleration and gravity, but you can, because if I were in a lift, for example, let's go back to the elevator in space with no gravitational field nearby, let me have two balls in that lift, right? If I have two balls in a lift, all that would happen is that they themselves would move with uniform acceleration and the distance between them would be the same. But the same is not true from the Earth. If this is the Earth here, the Earth's gravitational field is actually inversely proportional to the square of the distance from the center of the Earth. So actually, if you had the same experiment done on Earth, you'd actually see the distance between the two balls would increase because the gravitational field on the bottom ball is stronger than the top ball. Again, you may think, so what? But what it means is that you can tell the difference between acceleration and gravitational fields. So the equivalence principle holds over very small distances. You know, if these balls were basically right next to each other, there's very little difference in the distance, and therefore you couldn't tell the difference. But over longer distances, you can definitely tell the difference. And so, but Einstein, he doesn't want to give up the fact that his insight that acceleration and gravity should be kind of one and the same thing. And so he thinks, how can I therefore explain the presence of tidal forces? Now, this is where he makes a big leap, what will appear to be a big leap, but I'll explain some of the historical context of it. Let's take a step back. When you're taking a plane from Beijing to London, if you ever looked at the flight map when it's compressed into two dimensions, have you noticed that it's actually a curve, not a straight line? You may be familiar, if I want to go from A to B, I go in a straight line. That's the shortest distance, right? So why does a plane appear to take a curved path? The reason is because the surface of the Earth is curved. There's intrinsic curvature to a sphere, which actually means that the shortest distance between A and B on the surface of a sphere is not a straight line. It looks like a curve when collapsed to two dimensions. That's what we mean by curvature, intrinsic curvature. Now, Einstein looks at this and he thinks actually, well, this could explain the presence of tidal forces. How? Why does he come up with that idea? Well, just as on the surface of the Earth, if I look around me now, the surface of the Earth appears flat, right? It appears to have no curvature. This is a little bit like the equivalence principle. Over very small distances, the surface is flat, and therefore acceleration and gravity are the same. Over longer distances, however, there is curvature, and that's where the deviation starts to appear. And so what Einstein thinks is this curvature can explain two things. It can explain why over short distances, acceleration is equivalent to gravity, because space-time is flat, but over longer distances, why a gravitational field would be different from constant uniform acceleration, because you get that curvature, so you start to add little bits. Now, you may think, whoa, Einstein, how do you suddenly leap from the equivalence principle to curvature? Like, this seems like two very, very different things. And the reality is this, like, it wasn't completely from nowhere. A guy called Minkowski had already looked at special relativity and expressed it in terms of geometric equations. So actually, Einstein was already aware, although not particularly enamored with, the ability to express his original equations in forms of geometry. And he had several other mathematician friends at that time who, when he told him the thing he was puzzling over, they said, well, it sounds like a little bit like things we see in non-Euclidean geometry or curvature. And so they led him down that path. Einstein was also aware of other thought experiments, which you can look up as well. A very famous one called the carousel thought experiment that already told him that if space was completely flat, or as mathematicians call it Euclidean, there would be problems, Maodun, in his original theories. And so he knew something was going to have to change with the geometric representation of the system. So it wasn't completely from nowhere. So Einstein's here, he thinks gravity can be explained by curvature. So what does that mean? Well, it means that gravity must cause curvature in space-time. That's it. Which means the presence of a mass must bend space-time. That's the theory of general relativity. And why does that therefore explain objects kind of being deflected by gravitational fields or bending of light around objects? Well, it's like this. It's the same as the plane example. As soon as you've decided that gravity bends space-time, that explains those deflections. Because just like your flight from Beijing to London takes a non-linear path, a curved path, so would light in the presence of a gravitational field. So would a ball thrown in the presence of a gravitational field. To move between A and B, they actually follow the shortest path they can between A and B. Well, with curved space-time, that is itself a curve. And so that's the origin of the force of gravity. It's things moving along the shortest possible path they can, but in a curved space-time. And therefore it looks as if they're deflected. And that is the force of gravity. It's nothing more than the curvature of space-time. And that was Einstein's huge insight. In the next video, we'll just take this one step further and explain how actually you can predict the bending of light by gravitational fields from relatively straightforward thought experiments. And that'll be our third step into gravitational lensing.